Thank you for the introduction. Today, I will be presenting on peptoids inhibiting bacterial growth. So antibiotic resistance has been on an increase over the past decade. And though antibiotic resistance has a lot of causes, some major contributors are the overprescription of antibiotics, mutations in bacteria, patients not completing their medication, and overuse of antibiotics in livestock and fish farming, poor infection control in healthcare settings, and poor hygiene and sanitations. The image shown is the projection of the global working age population that is projected to be lost to the superbug in millions if this issue is not controlled by 2050. So it is seen that 100% resistance is expected by 2050 and 444.1 million persons will die as a result of antibiotic resistance. And what this essentially means is that by 2050, there will be no drugs that will be able to stop these microbes from multiplying and essentially causing death in individuals. More than 2.8 million antibiotic resistant infections occur in the US each year, and more than 35,000 people die. It is actually projected that the death toll will be around 10 million if this issue is not controlled by 2050. The image here actually shows the antimicrobial resistance mortality rate per 100,000 persons in the world. And it is seen that Italy will lead the world by 2050 in the amount of deaths occurring with 18.17 persons per 100,000 if this issue is not controlled. The US ranks second with 8.98 per 100,000 persons, again, if we do not find a solution to antimicrobial resistance. So peptoids, a family of peptidomimetics, have their side chains bonded to the nitrogen atom in comparison to peptides who have their side chains bonded to the alpha carbon. So what makes these peptoids so much better than peptides is the fact that this N-substituted amide actually makes it resistant to proteolytic degradation, which is very advantageous because that allows it to survive in the cell much longer and thus be able to inhibit lots of bacterial growth and be able to use for a longer amount of time. So peptoids are typically synthesized on a resin using solid phase synthesis. The synthesis typically proceeds via a repetition of amidation steps. First, an amide bond is formed with bromoacetic acid and dic in dimethylformamide. Then any primary amine can be used to substitute the bromine. Then the resin is cleaved and the steps can be repeated to achieve any desired length that you want. So in order to make these peptoids cyclic, they're typically made from their linear precursors and are synthesized on 2-chlorotriethyl chloride, on that's a resin, to generate a free N-terminal amino and C-terminal carboxyl acid, and then that is cleaved with hexafluoroisopropanol and dichloromethane in order to get your cyclic product. So the objectives of this project was to analyze the existing literature to figure out what structural characteristics of peptoids would be most efficient at inhibiting bacterial growth. In order to achieve this objective, JSTOR and ProQuest was searched using key terms in order to narrow down articles that were peer-reviewed and not more than 30 years old, as this was when peptoid research was on a rise, and that was when the most information was out about peptoids. So in order to establish this review, linear versus cyclic peptoids were compared. And in order to do this in this study, the researchers used a variety of linear and cyclic peptoids, and peptides were used as positive control, as seen with the linear peptide LGS and the cyclic peptide CGS that were used as positive control in order to provide comparisons into how well these linear versus cyclic peptoids actually performed. So in order to have this comparison, the minimum inhibitory concentration MIC was used to determine how well these peptoids are performing. What the MIC value is it is estimating the lowest amount of drug that can be used to inhibit the bacterial growth, and thus is synonymous with how well the peptoid is performing, which is its antimicrobial activity. So it is found that cyclic peptoids had a lower MIC value in comparison to their linear peptoids. And can be seen here, the linear peptoids are in blue and the cyclic peptoids are in orange. So it is seen across all 5 peptoids here that the cyclic peptoids outperform the linear peptoids and produced a lower MIC value in comparison to the linear peptoids. How they did this is that by making the peptoids cyclic, it enforced a conformational rigidity that increases specificity. And what that means is by making these peptoids cyclic and rigid, it was able to increase the cell penetration and thus targeting the specific area of the cell that was needed, the cell membrane, and not moving around the cell to other areas that would reduce its effectiveness. Another property that was investigated was whether or not lengthening the peptoid would make a difference in increasing the antibacterial activity. And it can be seen that with the exception of the hexamer C6, increasing the length of the peptoid does in fact increase the antibacterial activity. The prefix here, mer, refers to the number of residues used in the peptoid. So a 6-mer has 6 residues, an 8-mer has 8 residues, and a 10-mer has 10 residues. So it can be seen that the 10-mer performed the best in comparison to all the peptoids, which correlates with the idea that increasing the length of the peptoid does indeed increase the antibacterial activity and result in a lower MIC value. Another property investigated was whether or not fluorinating the peptoid would have an impact on the antibacterial activity. So in this study, fluorinated peptoids versus non-fluorinated peptoids were again compared using the MIC values and determined whether or not adding fluorination would impact the antibacterial activity. Compound 1 was actually not fluorinated to use as a control in the experiment, and all the peptoids had different degrees of fluorination, which will be seen in the table. So it is found that fluorination does in fact increase the antibacterial activity. And how it does that is by increasing the hydrophobicity, which is seen as synonymous with increasing the antibacterial activity of the peptoid. Compound 2 was found to be the most effective at inhibiting the bacterial growth across all 4 strains of bacteria. SA being Staphylococcus aureus, MRSP being methicillin-resistant isolate of Staphylococcus pseudointermedius, PA being Pseudomonas aeruginosa, and EC being Escherichia coli. The comparison that can be seen here is that compound 6 was also very effective and very similar to compound 2 in inhibiting bacterial growth across all 4 bacterial strains, and they also had the same number of residues. But what made compound 2 the most efficient at inhibiting the bacterial growth is the fact that, again, compound 2 was a longer peptoid in comparison to compound 6 that was a shorter peptoid. So it again enforces the idea that lengthening the peptoid does in fact play a role in increasing the antibacterial activity. All in all, cyclic peptoids are more efficient at inhibiting bacterial growth in comparison to their linear counterparts. Fluorination will in fact increase the antibacterial activity, but only to a certain point. Fluorination has a saturation point where adding more fluorine will only render the peptide ineffective because it will no longer be able to carry out its task. Increasing the length of the peptide as well does in fact increase the antibacterial activity. And in order to constitute the most optimal design of a peptoid, a combination of fluorination and elongated hydrophobic side chains would be best. Thank you.